So, lecture 4.4, modeling a real electromechanical system. So, don't forget, we're doing real stuff. Sometimes people complain about being in school and how, it's not real systems, they're all like theoretical. This is real. We're going to actually use these in the lab. So, very real. So now model the electromechanical systems from the lab, shown in figure 4.7. So I'm going to zoom in here. We've got these permanent magnet DC motors. Shafts comes out. It's a face-mounted DC motor. So there are two main types of mounting options for motors. Base-mounted, which would come off of this region here, and face-mounted, which comes off of the face of the... This is very dark up there, isn't it? The face of the motor in this region. So you also see there's this coupler here. So this shaft coupler is, if we zoom in a little bit more, maybe we can see, there are grooves cut in it, okay? And I'll kind of show you what this looks like from end on. It's a C shape. Well, that's a little exaggerated. It's a C shape. The shaft goes through here, and then you have through holes here for a screw to tighten it onto the shaft. So the two ends of these two shafts, so the shaft coming out of the motor and then the shaft that connects it up to the flywheel, are clamped down on. And the coupler is there, so there's a couple things. Usually we don't want to load the motor shaft itself with something that weighs quite a bit. I think the spec on this is like 10 pounds you can hang off of the end of the shaft. Even if you are within spec, it's generally not a great idea because you're going to wear out the bearings on your motor much faster. And typically it's easier to replace and cheaper to replace the bearings that are outside of the motor. So we usually don't want to put a lot of radial load, that's what it's called, on the shaft of the motor. So we typically couple it to something else that has weight bearing bearings, weight-bearing bearings. And that's what we have here. So we have to couple the shaft. Also, there's often not enough room to really get a good amount of connection between your load and the direct shaft from the motor. So often we're going to use a coupler. These couplers allow you to have a little bit of misalignment between the two ends of the shaft. So, for instance, you could have two shafts that you're trying to couple that are a little bit off, and that's too drastic, it wouldn't work, but you can do a few degrees. Some of these couplers will allow you to do like maybe up to 10 degrees would be a really flexible one. They have a little bit of flex in them from these grooves that are cut, and that can be a good thing for allowing the alignment to be a little bit off. As you know, when you actually build something, even if you say the tolerances are this and that, is only so close that you can get to being perfectly aligned with your two shafts. So the coupler needs to have a little bit of flex in it. That flexibility can cause issues if you end up worrying a lot about precise position control at high speeds. So if you have a flexible coupler, you have to take that into account in your system. You can get this oscillation that can happen. Sometimes it's not great, but in this case we are using stainless, which is pretty stiff. Usually does not have a lot of flexibility, even these shaft couplers. Now, these ones are expensive. So stainless ones are expensive because this part's hard to manufacture. Aluminum ones are cheaper, but they break easier. And also, you guys haven't gotten there yet, but when you get to machine design class, you'll talk about fatigue life of different materials and parts made of different materials. Stainless, well, so steel has, if you don't load it above a certain threshold, you can actually reload it over and over again, and it doesn't fatigue fail, or at least it won't for, a very, very long time. Whereas aluminum doesn't have this sort of infinite life threshold. So the curve that you'll calculate, it sort of levels off for steel, so you can just keep loading it for, more and more and more cycles, and it won't fail as long as you don't go above a certain threshold. Whereas aluminum doesn't have that, and it just fatigues. Even at low loading, it fatigues. So for a part like this, it's gonna you're gonna cyclically load this thing for a lot if you run this very much. Aluminum couplers are more common and way cheaper, like 10 times cheaper, but they will fail eventually, which is why they're always replacing aircraft parts constantly, because they're made of aluminum to be light, but they are going to fail. It's not a question of if, it's when. So yeah.
So with those parts, if you remelt them down, then does the fatigue kind of reset?
Yeah, you can reuse the metal. It's just the essentially the micro structures get messed up. They're like these micro cracks that can happen, and then they tend to start to fail at that point. And the fatigue stress is really a very experimental field of study. So they do tons and tons of tests, and different alloys have different properties, and then there's like the stress concentrations that come in. So you can calculate things, but they're always sort of estimates, and then you have factors of safety, and you have confidence intervals and all that. So it's a challenge to work with fatigue, but it's something that it's good to start thinking about now. Next semester, you guys will get into more detail on fatigue. And then we've got this other shaft that has two bearings here. You need two bearings if you're going to be able to hold any moment, right? So two bearings in here, and then we have a flywheel. Flywheel is there to be a sort of simulated load. You could be driving something that has some big, heavy mass associated with it. In this case, we put that on there to have some sort of realistic load on the motor. I mean, motors can do amazing things when they're not connected to anything. So put a sort of realistic load on it. And also, it's not dangerous, except please keep your hair away from it, because it's not pretty if your hair gets caught up in the shaft, and it'll suck your head down. Fortunately, I don't have any sharp parts, so you're not going to get cut, but you will be missing a chunk of your hair, so that would suck. Okay, so this, I give some specs on this. So the specs on the motor, it doesn't have a motor curve, and we're going to talk about motor curves. We're going to actually generate a motor curve for this motor. But these are the types of specs that you would see in a typical permanent magnet DC motor manual. And I transcribed them from the manual, and I also put in an SI conversion for each one. So there are things like continuous stall torque, peak torque, max terminal voltage, max operating speed, the rotor moment of inertia, the damping constant, thermal resistance, max armature temperature, max radial load, 10 pounds, like I said. The torque constant and the voltage constant, so they're given in inconsistent units, and then when I convert them to SI units, they come out with the same numerical value, which is nice. Terminal resistance is 1.6 ohms, and that's not too bad, pretty low, and has armature inductance. Max continuous current is different than the max peak current. So the continuous current is way lower than the peak because it's pretty much limited by heating. So if you heat too much, then you're going to end up burning up your coil and ruining the motor effectively. So you can run continuously at 4 amps without overheating because the heat will dissipate in time. But you can very short bursts go up to 34 amps. I give a lot of the sort of mechanical properties here. So moment of inertia of the flywheel I give. We're going to use this model here for the motor with a voltage source associated with it, and we'll say that J is going to be both the motor moment of inertia and the flywheel. We're going to assume that the coupler is stiff, completely stiff, and is not flexible at all. But I do, in problem 481, I draw a linear graph of how it would look if you were to include the flexibility of the coupler. For our purposes, it's effectively perfectly stiff. But if we had certain applications, we might need to worry about a flexible coupler, especially if it's an aluminum one and you're doing precise position control that has time as a factor. You're going to need that. And then, so what we're going to do then over the next week and a half or so is, in lab this week, you guys are going to be taking some measurements with this. In class, we're going to be modeling it, and we're going to hope to see an emergence of the experiment that you're doing in lab and the theory that you're doing, the predictions that you're doing in class, coming together. And I think it's pretty fun. We're going to estimate the essentially the motor constants for this motor from the measurement that we'll do. So it'll be fun. Okay? All right. See you guys.